everyone can sign up. There will be people still coming, so we'll give a few more seconds, not minutes, a few seconds.
Okay, that's fine. It looks like everybody should be able to participate and come straight in now. So I'll hand over to you, Yulong.
Great, thank you very much. So first, welcome to this specific session of the Cross-Hub Conference, and this is the first day, and is from our energy storage, Supergen Energy Storage Network Plus program, and we're hosting this. And so I'm going to just give a welcome. Thank you very much for joining us. And there is some housekeeping to do, and it's easy because there's no firing alarm, whatever it happens, and so just need to still keep quiet and probably mute yourself, and unless you're talking. And so today's main meeting is about role and value of energy storage technologies for net zero 2050. And so Dr. Harris, I can't even pronounce his other part of the name. It's very long, and we've have been trying, but anyway. So Harris will chair the first part of the meeting on the storage technology, particularly for various aspects from heating, cooling to transport and to power system. And so without much ado, I'll hand over to Harris. So the floor is yours, and the rest of the speakers.
Thanks, Yulong. Well, as Yulong said, we have a panel session planned for today, and the role of storage to net zero. So we've got three experts from different fields: transport, heating and cooling, and power. And we also have a representative from BASE, so we'll cover hopefully some policy aspects. So the idea is that we'll have three presentations, and then we'll open up the room for questions and answers, but also for a discussion. Before that, I'd like to share my screen and make a very short introduction about the Supergen storage network. So hopefully I'll manage to do that. I think I've now shared my screen. And okay, so my name is Harris Patsios. I'll be chairing this session. I'm a co-director of the Supergen Energy Storage Network Plus, which is quite new, I would say. Unfortunately, we just started a few months before the pandemic, so a lot of it has been, a lot of the road has been a bit hurdly. At a glance, the network is led by Professor Yulong Dean, who opened the session from the University of Birmingham, but gathers 19 academics from 12 different institutions. We've got a total of 1.2 million of funding, 1 million from EPSRC, and quite a sizable amount of that is dedicated for flexible funding. So we're not so much in mission to do research, but actually fund research, but also bring the community together. We've got strong in-kind support and a range of project partners who are actively supporting us in this endeavor. So we've got 48 months in duration, having started, as I said, in September 2019. Now, the reason why we've put together this network is because we felt there was a gap. There's some fragmentation, although we have a lot of funding in storage, a lot of activity, especially in the UK, and we're in a position to be world leading in that domain. There's still quite a lot of fragmentation, not only between disciplines, but also between academia, between industry, between decision making, government. So the intention is to bring everyone together to serve the community by bringing everyone together and create an ecosystem of different disciplines, different entities, different stakeholders, understanding the need to bring all that together, because storage doesn't only cover a lot of technologies, but also brings together, or should be bringing together, a lot of disciplines. There's a lot of impact to be had, so we do intend to bridge that gap. Now, as I said, we are working across technologies, not only in one technology, but we cover many technologies like electrochemical storage, electrical, thermal, mechanical, and chemical. And we're not only interested in storage itself, but the integration of that into energy networks, the impacts on society, the impacts on the technologies, and vice versa, environmental, economical, and policy considerations, and topics like artificial intelligence and big data. So some of our activities short term include exploring potential for joint flexible funding calls. A lot of the time we try to do that jointly, as we've done in the past with other UKRI hubs and institutions. We have targeted workshops to promote building and promoting relationships between industry and academia. And we hopefully have managed and are still continuing to advance and nurture early career researchers by bringing or creating forums. We intend to continue doing that on a more long-term basis, support early career researchers, target funding to promote underrepresented groups, or join up larger consortia and address more significant challenges that, as I said, often are interdisciplinary. I'd like, before I close, to bring your attention one of the next workshops we're going to be holding. That's on the 15th of September. It's mainly focused in promoting relationships, as I said, with industry. So it's vision, challenges, innovation, and deployment and experience, where we'll try and highlight business and market needs for attracting investment on storage and speed up relevant applications. There's quite a lot more information in our website, supergenstorage.org. So I welcome you to have a look and get in touch with any questions. Now, we've got a lot of means of keeping in touch with you. I've listed some of the social media, but also website links here. And Angela Fifka is always happy to answer your questions regarding the network or any other activity we might have. So please feel free to get in touch. I'll now stop sharing my screen, and I think we're ready to introduce the first talk. This is going to be from Professor Andrew Cruden on transport. So Professor Cruden is a professor in energy technology within engineering and the environment at the University of Southampton. He has significant experience in the field of renewable energy, particularly in fuel cell technologies and condition monitoring of wind turbines. The interest in fuel cell technology led indirectly to an interest in the field of electric vehicles, and subsequently to research activity in energy storage, both batteries and supercapacitors, and traction drives, and through a lot of EPSRC and TSB funded projects. So, Andrew, I'm not sure if you're ready to share your screen.
Just to be clear, I'm sharing my screen, Amma, when I present. Is that correct?
Sorry, say again, Andrew.
Can I just check that I'm sharing my screen?
Yeah, if that's okay, I think you should be as assigned as a presenter. But if
give this a go, that's fine. Let me just see if I can bring this up. Hopefully that's now presenting, is it?
Yes, it is.
Excellent. Okay. Good stuff. So I believe I have 10 minutes on this.
Yes,
So,
that's
and
correct.
again, I was asked to talk about transport. So let's make a start. So just to start with some context, clearly there's a large government and societal interest in reducing greenhouse emissions, particularly in the transport, and that is predominantly being done through the process of electrification. So clearly the UK has legislated it's going to end the sale of new petrol and diesel cars by 2030. It's currently consulting on a date for phasing out the sale of new diesel HGVs, so again the larger, more freight-based vehicles. And again, if that first element is on road transport, then there are other similar activities happening, probably at different pace in the other transport sector. So rail, again, rail is aiming to remove diesel-only trains or take them out of service by 2040. In maritime, the International Maritime Organization has a target of a 50% reduction in greenhouse gas by 2050. And in aviation, again, currently they have introduced sustainable aviation fuel, which is effectively a renewable, or in lots of instances it is a kind of waste-based element or a biofuel for that. I'm currently exploring Fly Zero, so there have been a number of elements and demonstrations of electric and fuel cell planes as well. So lots of activity across that sector in terms of electrification. And again, just to put it into context across those different sectors as well, by far and away the largest contributor to carbon dioxide emissions from the transport sector is passenger cars. So clearly that's where, again, most of the activity has to be focused, and that's where the greatest market opportunities are as well. And this graph hopefully gives you some flavour of the different percentage emissions from those different sectors. Again, just in terms of scale as well, the global battery demand is expected to increase by some 14 times between now and 2030. So again, a significant rate of expansion, probably 20% average growth per year. The global battery market, again, an estimate, they feel it's something like $150 billion by 2030. And again, just to put that into context, if that's the battery market, clearly one element within transport is hydrogen and fuel cells. So just to give some idea of scale, again, that global fuel cell market is forecast to hit about 9 billion by 2030. So just to give some sense of scale for that. And the market for EV batteries is already 10 times that for grid scale batteries. And again, I know there's going to be a subsequent talk on more of the grid scale activities in just a few minutes. Again, in terms of performance requirements, I would direct you to some very good roadmaps that the Advanced Propulsion Centre has produced. If I would just try and see if I can bring up my pointer. There we go. Again, we have a graph here from this is the kind of automotive roadmap for batteries. Again, in terms of energy storage, we have energy and power, and clearly we have, in terms of the colouring here, light duty vehicles, again, really vans and passenger cars. In terms of the power for example, sports cars, etc., down to more normal passenger cars, is probably down in the left-hand side of this sector, compared to, for example, this light grey sector, which is really the heavy goods vehicle, where clearly power is a major requirement, again, in terms of moving these heavy loads, and energy in terms of the range for it. So to give you some metrics in terms of that, again, the definition of those metrics is in the roadmap, so let me direct you towards them. And although this is an image from one of the battery or the energy storage one, there is a separate one for fuel cells as well. And again, just a bit of flippancy. The reason I'm putting these up is, as well as cars and other vehicles, effectively electrification, both batteries and fuel cells, have been used and demonstrated in a whole range of different transport applications. So everything from a lawnmower, obviously submarines have had batteries and fuel cells in it for a large number of years. So this technology in lots of instances is not new. It's about refining it, reducing the costs, making it reliable, and getting infrastructure in place to support it. One of the other aspects, again, in terms of transport that's fairly recently been flagged, is there's increasing and growing concern over the anticipated volumes and therefore the processing challenges of end-of-life batteries, particularly the lithium-ion-based ones. So clearly, as most manufacturers have already announced significant plans to go electric only, or to go and promote new electric models, the battery capacity that we're going to see in our roads, and given that a typical vehicle lifetime for a passenger car may only be between 15 years, something like that, again, the processing required to handle the end-of-life batteries and ideally try and recover as much of that material as we can is critical, and currently we don't really have that capability. So that is something that, again, in terms of trying to prevent this material going into landfill waste or other waste streams, is to try and make as much use of that and recovery of that as we can. And to do that, again, there's increasing regulation being developed. So only late last year, the EU has proposed, and I know we are not strictly part of the EU, but I'm sure we will follow a number of their the regulations and develop our own in a similar fashion to try and up the targets and the rates of collection of batteries, again, including vehicle batteries, which tend to be, dare I say, fairly straightforward to do because it is a tracked product from both manufacture, licensing through the vehicle registration, the V5, the MOT process to end of life and scrapping. That's regulated, so it's fairly straightforward from that perspective compared to consumer batteries, which are much more difficult to track. But in terms of upping the rates for battery collection and therefore the recovery rates of taking a battery pack from a vehicle, you then have the outer support and enclosure for that, all the electronics for the BMS, you might have a thermal management system in there, the various connections as well before you actually get into the various cells and the elements of recovery. You then have different chemistries to deal with that have different constituent elements that might be tried to recover as well. So again, legislation is clearly coming in terms of mandating in that, and that is a challenge for transport energy storage per se. Again, I think a key element in transport is thinking of the numbers of vehicles that we have and this increasingly rapid transition to electrification. Again, we will end up with significant capacities of batteries on our roads and therefore parked at various times as well for recharging. So again, I think one of the key aspects of energy storage activity is linking that transport capacity to some elements of the grid requirements for that through, for example, vehicle to grid, where we're aggregating EV batteries on a substantial basis as the numbers of vehicles and the charging capability increases as well. Now, there are a number of fairly sensible trials going on, one with OVO Energy and a bus-based one with Scottish and Southern Energy, and they are UK ones. There are other examples of this around the globe. And again, the good thing about this is battery technology neutral. So again, I think in lots of instances we will have this capacity and we can use that capacity to support the grid, again, regardless of the technology we actually have on the vehicle. And again, in terms of some of the future look, clearly lithium-ion technology is dominant just now. There are new technologies and new developments in technology ongoing. This is just one example of the Solbat project funded by the Faraday Institution, where again, rather than some lithium salts, we're now using lithium metal, which again will have its own challenges when it comes to the recovery of that metal from used batteries, if and dependent on the ultimate commercial prospects for this once it's coming towards the end of its research phase. But again, clearly we can see some of the projected benefits of this technology being increases in both gravimetric and volumetric energy density, and therefore the vehicles themselves should be lighter, and therefore the performance and range should be better as well. Just lastly, just to try to conclude, again, effectively there does remain a very clear technology race, both in batteries per se, in terms of the different materials that are used in the whole range of different lithium chemistries, as well as new including silicon and sulfur compounds, multivalent batteries as well as then battery versus hydrogen fuel cell technology. Significant growth in global government support. Again, subsidy is delivering that change. So again, we can see many reports in the media about this change that's happening right now. Again, I've flagged the waste and processing challenges of these end-of-life batteries. And again, I do think that vehicle to grid will enable a better linkage between transport, energy storage and grid energy storage requirements. And I think I'll just finish there. Thank you.
Thanks, Andrew. I guess we can, as I said, have questions at the end after every presenter has a chance to speak, but thanks for the very interesting talk. Next, we've got Professor Zibin Wu from the University of Glasgow. His interest is focused on thermal energy technologies and their fundamental thermodynamics, heat transfer, fluid dynamic problems. He's particularly interested in developing novel technologies for heating, cooling, and power generation. And I think he's gonna be telling us more about this just now. So,
can you hear me and can you see my screen?
Yes, we can hear you and see the screen. Thanks.
Okay, thanks for the introduction.
Over to you. Thank you.
Thank you very much. Thanks for the introduction and thanks for giving me this opportunity to share some of our thoughts about the role of the thermal energy storage in the future net zero world, particularly heating and cooling. And I guess most of you have already seen these figures probably a few times somewhere else. So this gives us a very visualized view about how the heating problem is. So particularly heating probably consumes about half of the energy consumption in the UK, particularly 55% in the Scotland, even worse. And so what's making it even worse is that it's fluctuating all the time over a year compared with the electricity. And so it's much more fluctuating from summer to winter. And if we zoom in a little bit more to see the details, so let's say we take 1 year from say May 2015 to April or May 2016, and we have a look how this fluctuating look like. So it starts with the minimum about say 400 gigawatt hour per day, and it changes from the summertime, the August time, to the winter time, say January, with about 2,300 or 2,500 or 600 gigawatt hour per day. So if we look, this minimum demand that is pretty much weather independent, probably will be more likely related to cooking hot water or some industrial applications. So where there is a very strong time variant changing variation component that is weather dependent, this is very likely due to the consumption for the space heating. So if we assume the all weather dependent gas consumption as the space heating or heat demand, so we are talking about the fluctuation from 0 to 2,300 gigawatt hour per day. And so that is a huge gap there. So if we look at the total of the year, this roughly gives us the total heat demand for the UK per year will be 400 to 450 terawatt hour. And if we think we can have magic technology with 100% interseasonal energy storage, and we produce or gather heat in the summertime, and then somehow discharge it, release it for heating in the winter to basically balance the demand to shave the peak, and then we roughly locate about 50 terawatt hour capacity. So there is a huge potential here, a huge opportunity or challenge, whatever, about the interseasonal energy storage for heat. And if we look at the further zoom into a day, So here we take an example, say we take a few houses or properties in Scotland as an example with relatively poor insulation, and we look at the heat demand over a day. So we can see there is not even. So in the early morning, and when everyone got up and then before they go to work, so there is a peak demand. And also there's another peak demand in the early evenings when everyone come home and before they go to bed. So again, there's a peak of demand here. So again, there's an uneven demand of heat demand, heat supply, space heating. And so that will require some sort of short-term thermal energy storage to manage the demand and supply, at least to shape the peak. So now the question is really interesting for us is how big that scale would be in terms of the whole UK, and particularly in 2050, we are targeting to reach net zero in 2050, and the scale of the problem is huge because half of our energy consumption is heat. So that we need to basically break down the heat demand to hourly or half-hourly data to look at how much heat we will need per day. And so that's what we did. So we actually tried to develop a model. So this model, we just take the whole UK building stock and put them into a model, a physical model, and we call the bottom-up model, and using a design builders and energy plus. And then we put all the weather conditions and insulation level into it. And so the weather conditions are different from one part of the UK to another part. So basically we split the whole UK into 8 different regions, and according to their weather patterns. And in this way, we can then actually calculate the heat demand any hour of the day. And for the whole UK, when we add them together, we roughly can work out the hourly heat demand. So before we using this model to calculate the heat demand in 2050, we actually use this model to calculate the heat demand of 2010, because we knew that gas consumption data, and also there's another model developed by a Loughborough team, Stephen Watson. So already broke down the gas consumption to heat on hourly base. But what they did was use an approach. They gathered the gas meter data from about 6,000 properties and then use that as a reference to break down the total gas consumption to hourly heat demand. But this model has a problem because you don't have the gas meter data in 2050. So you cannot predict 2050, only can analyze the historic data. So we then actually developed this bottom-up data model then to compare with this model to verify it. And here is the comparison between the two models for 2010. So it looks a very good agreement. So then we got some confidence. We then actually use this model to find out the hourly data, heat demand for, let's say start with 2010. This is a very cold year in recent years. And then we actually worked out, the heat demand, peak demand is in January, a particular day with about 300 gigawatts. And the total heat demand of the whole year is, including both space heating and domestic hot water, is estimated as around 415 terawatt hour. This is pretty much close to the rough estimation using the gas consumption data in the previous slides. So now we actually can use this model and to predict the heat demand and the hourly heat demand of 2050 for the whole UK. So we need to take into account a few different things now, because there's a global warming, so the temperature will increase year by year to 2050. And also the legislation of the government have required us to improve the insulation of houses and the properties. So here we actually selected a value of 30%. So 30% improvement of house insulation. And also there will be new houses come to the market. And so in general, the heat demand actually decreases slightly or significantly, I would say. And so the peak heat demand actually now, according to the predictions in 2050, after the global warming and the insulation improvement by 30%, will be about 175 gigawatts anytime. And the total annual heat demand for space heating and domestic hot water, so now can be estimated, predicted as about 250 terawatt hour. So again, you can see there's a fluctuation between from month to month and from hour to hour, if you look at this direction. So now, because we are talking about the electrification of heat or the heating decarbonization, so obviously at the moment, as you know, BASE is looking at the possibility of electrify heat using heat pumps, and that is the main route at the moment. But I'm not saying not other routes are not possible. It's just is one of the possible routes. So let's assume we use heat pump and with a COP of 2.9 to produce all the heat to meet the demand. We then say take 2010 data as an example. We convert to take this heat demand divided by 2.9 and add the electricity demand the same year. So we end up with the total electricity demand peak will be 150 gigawatt. And so that year, the electricity demand is only 50 gigawatt. So that means you will triple the peak electricity demand because of the electrification of heat. And considering the currently installed capacity of about 100 gigawatt, that means we are talking about you need to install 50 gigawatt new power generation capacity. And that is not going to work because it's too expensive and you only use them in winter for a few days without using it in summer. So that doesn't work. We need to consider, you know, storage and flexibility to shape the peak demand. And if we look at, put this in the scenario of 2050, according to the prediction we made. So what will look like is in 2050, they predict the heat demand peak in January will be 170 gigawatt and somehow in this range. And the national grid also predicted the electricity demand in 2050 will be around 100 gigawatts. But that has already taken into account the electric vehicle, but I'm not sure whether they have already taken into account the heat pump electricity consumption. So it's uncertain there. And so if now we convert all the heat demand through heat pump and with a COP of 2.9, we divided the blue line by 2.9 plus the orange line. So we end up with this total electricity demand with a peak demand of about a 130 gigawatt. So again, if we take it, compare with today's 2020 installed the capacity that was 100 gigawatts. In any case, we are still talking about you need to install another 25 to 30 gigawatt power generation capacity to only for the heat pumps. So again, this is huge, and it's probably not feasible or viable in terms of the scale. So what we actually will do is now actually, if we look at a particular day, let's say the maximum heat demand day of a day for the UK in 2050, what you can see is the heat demand actually fluctuating very significant over the day with a big peak in the morning time and the early evening time. So are we going to use electricity anytime we want, or we actually can use the heat pump to produce heat the whole day, but store it when we don't need it? In that case, we can somehow shave the peak demand and reduce the impact to the grid. So when we look at this, we can roughly estimate the scale. And according to this diagram, the domestic heat, including the space heating and the hot water in 2050, this roughly gave us a figure, say 100 and 250 gigawatt hour heat storage we will need, and to shave this peak. So that gave us roughly the idea in 2050, how much heat storage we will need to shave the peak of the heat demand in the domestic sector. And so that is about from the perspective of heating decarbonization or electrification. And also, as the global warming kicks in, the temperature will increase. Actually, another headache will come is the cooling. Particularly this year, I think in the south, particularly in London, the cooling was a big problem. So there also a report recently published by UKirk estimated in 2050. So in the highest scenario, there will be the electricity demand in early evening will be increased by 7 gigawatts. and one also was from the University of Birmingham. And this will add to the problem as we just explained in the heating sector. And so again, as you can see, the demand of the electricity curve has been dramatically changed due to the cooling demand. So again, there is another possibility we can use cold thermal energy storage to manage to balance the demand and the supply and to shape the peak and to reduce the impact to the grid. So roughly, a very quick kind of introduction, say from a perspective of a heating angle, and so here is a very quick remarks to conclude in my discussion. So both of the heating and the cooling will impose huge impact to the grid, and we need storage to provide the flexibility to mitigate this impact. And the scale of this is huge. It's, as I just explained, it will be tens of gigawatt scale, and also both the interseason and long-term storage and short-term storage are essential both for this to address this issue. And of course, cooling will impose some challenges, but it will be less than the heating problem. And again, the cooling cold thermal energy storage can also play a big role in the future net zero cooling system. Thank you very much, and I think I need to stop now. Thank you.
Sibin, as I said, we'll park questions for the end, but I think the closing remarks will take us nicely to the next talk from Professor Jihong Wang from the University of Warwick. Jihong is a professor of electrical power and control engineering and the School of Engineering, and her research interests include power system modeling and control, energy storage and grid integration, energy efficient actuators, and optimal control methods. So Jihong, whenever you're ready, we can see you. I hope you'll be able to share your screen as well.
Okay, I just share my screen. Okay, so yeah, can you see my screen now?
Yes, but
okay.
not in presenter view.
Yep. Okay.
You can just.
Yeah. No, it's
perfect.
Okay. Yeah.
Thank you.
All right. Okay. I think I try to finish in a short time. And the presentation, I just use the title given by our project manager, and so the presentation is representing two of us, me and my colleague, Dr. Wei He. Wei He is now a senior research fellow, hold 5 years Royal Academy of Engineering fellowship. Okay. So, let's start from this. That's yesterday's UK energy power generation source. And from this yesterday's, we can say we have a fossil fuel and wind, solar, and other clean energies. And that's a combination of this. And also we can see the demand change it is recorded every 10 minutes. And so this gave the grid, national grid or grid operators a big challenge, and because we need the electricity generated must meet the demand, that must be balanced to maintain the grid operation stably. So that's last month and last year's and the generation. To maintain the grid balance, I need a lot of mechanisms and strategy, and again, it's very costly, and that's the cost from 25th August this month, last month, and that's how much spent on maintaining the grid balance, and so that's the energy need to maintain the balance. So they can't change it, and that's for 25th August. A single day maintain grid balance, the cost 5.59 million. So this including frequency control and the positive reserve and negative reserve and others. Anyway, that's combined, that's the cost for the day. With the cost that indicate the need. So this need and is trying to and balance the grid generation and the usage. And so we need some energy to dispatchable. And traditionally, all this been done by fossil fuel. We store energy in the fossil fuel. When we need, we just burn it and then get the power. But now need multi mechanisms, and certainly that's come to see. And this kind of need and also increase when we have a more renewable energy, uncertain and intermittent renewable energy into the grid. That's 2005 to 2014, and the balance cost increase. But look at the now. And there's a prediction from National Grid website. The predicted in December 2020 is needed 2,000 million pounds for grid balance in next year from December 2020. But when I checked the figure in August, and there's a new prediction, 2,357 million pounds needed for next 12 months. So that means when we have more and more renewable energies and intermittent energy generations into the grid, we need more such kind of balanced service. And this certainly created a market, created a need to give energy storage room and to get into this market to provide the service. So, and look at globally, that's a battery energy storage installation. In the UK, by end of 2020, there are around 1 gigawatts battery storage in operation, and also another 4 gigawatt storage project in planning, some in construction, some in the planning stage. And this map shows the UK battery storage side. And so the largest battery energy storage plant in the UK now is 100 megawatts already in operation. And this storage side is recently got permission to be extended to 150 megawatts. So all this battery storage need and with a good market and attract investment, and looks at in the UK going well. But all this is really serves the daily, second, and the instant balance of the grid. But when we look at the 2050 to achieve net zero, we really is trying to get rid of this brownish color in our generation, to get rid of all the fossil fuel and to use all clean energy. But when you look at the wind, this blue line, in early August last month, and in this a few days, we don't have much wind. And so in that case, energy storage for short-term storage and this balanced service, probably not enough to change this gray area in our generation into green or into other colors. And so for deep decarbonizations, we need more strategies or other type of energy storage. And that's another simple diagram. And at the moment, that's our greenish energy generation. That's the demand. In between is use other type of energy to balance. In the future, if you have a lot of non-dispatchable source from renewable, from clean energy, and then we have a problem because that's our demand. And sometimes we need a very big gap in between this demand and also generation. We either just simply install more and more and not just meet the peak demand, but much more than peak demand of the power generations plants. But that's very costly, and they give you very low power factor, only use very low percentage, not economic. And so that means, in addition to this short-term fast response grid balance energy storage, we need long-term and long duration storage. This study indicated when we increase the percentage of renewable energy, and the energy storage we need will be increased as well. And also the increase is not just short-term, but also daily, weekly, and seasonal, and the hours, how long you need to store. And then to achieve this significant decarbonizations. So this is true, and if you look at recent national grids and future energy scenarios predictions, and no matter in which way we achieve net zero in 2050, either customer transformation, that means we have a lot of change to electrical car and change to electrical heating and whatsoever, and all system transformation introduce a lot of hydrogens, or fastest way to phase out of a fossil fuel, and this purple color all over there, that means that storage need. So to achieve net zero in 2050, and definitely energy storage is inevitable, even with this high terawatt hours and hydrogen energy storage or energy available. We still need those big and energy storage. So look at energy storage technology. There is various options, and then this is the figure apart. This gave the time and capacity comparing which one more suitable to which area of which purpose of usage. When we look at large and long durations energy storage, there is various technologies, and compressed air, liquid air, and pumped hydro, and other thermal storage, hydrogen, and that's quite a lot of technologies. And also any technology comes with a cost. So that's a comparison, this capacity and various technology and the cost, and for various technologies. And with these comparisons, and so with this kind of cost and the capacity, definitely need more study to see which ones gave better solutions. And there's a recent paper we published. They did some initial studies, and then certainly use this opportunity. I would quite trying to say a few words more about compressed air energy storage. And for compressed air energy storage, and it's use electricity to convert to use compressor and increase air pressure stored, and then the generations we need. So this compressor energy storage has two kind of weakness. One is low energy density, but when we look at the UK, in the UK we have a lot of salt cavern deposit.
Ji-Hong, I think you're muted. So Ji-Hong, if I'm not sure if you can hear us, but you're muted. So if you could just unmute yourself unless there's noise.
Oh, okay. Sorry.
Now we can hear you. Okay.
I think I moved my headphones. That's a problem.
All
okay.
right.
Okay.
No worries. No
okay.
worries.
Yeah. Okay. Yeah. So just quickly come back. So that's UK. We did a study with the British Geological Survey. That's UK potential. We have a rich salt deposit to be able to engineer into salt cavern to store compressed energy. Even we just simply use 1% of this, we would have such kind of a big terawatt hours storage capacity. That's already existing cavern. That's potential in the UK. So, and then based on this, we did another study and just say if we use existing cavern to store compressed air, suppose we have a compressed air and energy storage in place to replace the current gas power plant, and that's how much energy we can provide and to replace this gas power plant, and that's also in the paper. And for the salt cavern potential, also there's new paper published recently. So to end this presentation, and it's no doubt we need energy storage, massive energy storage, and with various scale and durations to achieve net zero 2050. For fast response energy storage, and the market is viable in the UK, and a lot of people want to invest into it. I have 3 past PhD students working in this area. 2 are building a storage plant, and 1 operation, maintaining operation plant. And so there is a good market, but we need large scale and long term and to achieve this goal for energy storage. But the market proposition is not clear. And the recent long duration coal from base, and 1 company is interested. We work together initially trying to put a proposal in, but after all the financial calculation, they feel takes probably too many years to get the investment back, and didn't submit the project. So I think this really for long duration storage, if we UK still need to think about it, to how can we make a little bit of change to favor various technology to put in place for 2050 net zero goal. Okay, I stop here. Yeah.
Okay, thanks, Ji-Hong. I think we can move now to the panel session, where we will be also joined by Dr. Bart Leeuw, Head of Smart Energy Innovation and Innovation for Climate and Energy at BEIS, and also Dr. Yongliang Li from the University of Birmingham, who's going to be replacing Professor Zibin Wu, who's unable to join, unfortunately, the panel session. But Yongliang is a reader in the School of Chemical Engineering, and his research interests focus primarily on thermal energy processes and systems, so quite close to what we heard from Professor Zibin. So, Bart, I wonder if you want to give us a couple of high-level comments from BEIS's perspective on these challenges.
Absolutely, yeah. Thank you very much, and thank you for inviting me, and thank you to all the speakers for excellent talks. And I think they all really present very clearly the challenges ahead, but also, I suppose, in a way, the opportunities. Storage and flexibility, which are the areas that my team cover, in a sense, are complex compared to many of the other areas within our innovation portfolio, because there's so many different moving parts and possible avenues. To say a bit about the importance of storage, I think it's clear from these presentations, and to BEIS, it's clearly a very important area as well. We see it as having a major potential in not only decarbonizing our system, but doing so at a minimal cost to get to net zero, particularly through taking advantage of intermittency and reducing curtailment in the offshore wind area. It's come up as a key statement, support statement in terms of the Prime Minister's 10-point plan, as well as the recently published Smart Systems and Flexibility Plan as well. And these also try and draw out where some of the challenges might lie ahead. There's been significant progress over the last few years, but it is clear there are still challenges ahead, and I'll talk a little bit later down the line about the consultation that's currently out. But it's also worth remembering that storage is more than often large scale storage. I think Andrew touched on the V2G opportunities there as well, which we're also very keenly exploring and looking how we can overcome those challenges. My team in particular looks at energy storage and flexibility. The most recent relevant activity is the £68 million long duration energy storage program, which in itself demonstrates that this is an area that's very important to us. I can't say too much about that in particular, as it's a live competition, but hopefully most of you would have been aware of that before we got to the close of that. And that looks at the breadth of storage possibilities around electricity storage, thermal storage, as well as power to X. What's clear is technology isn't the only challenge here, and I think all the presentations touch on the financing and the markets and everything else, and particularly when you get to the scale of the projects that we look at supporting, those financial aspects then make it more challenging when you get to close to pre-commercial projects. The base recognise this, and my policy colleagues obviously are aware of this as well, which is why they currently do have a consultation out looking at these challenges. And I do hope most of you are aware of that, and if not, please do look on the .gov websites at this consultation, which closes 28th of September, which looks at how, questions on understanding a lot of the challenges that the panelists have, not the panelists, the presenters have discussed around the market, and how is flexibility and storage valued in the market, how they might be addressed, and the risks associated to the various options. So if you haven't done so already and have views, please do participate in that consultation, because that is a direct way to inform government on a broader set of views, and then potentially influence the policy going forward, which is important for all these, particularly storage technologies, and our own program as well, in terms of the innovation program that rely on it. So yeah, in short, all very important. The challenge is clear, but also the opportunity. But there are a number of levers that government need to work with industry to make them sustainable in the long run, I think.
Okay, thanks, Bart, and thanks for the excellent summary of these points. I'd like to thank the speakers once again and move to the questions in the order they appeared, and I'll try to bundle a few because we don't have a huge amount of time. Starting from how they appeared, there's a comment on Orkney and also about fuel poverty. So I wonder if perhaps Ji-hong or Yongliang can pick this one up and make a few comments about fuel poverty, because I think this is quite an interesting aspect, and storage could help a lot with that.
Okay, and it's not my area. I think, but the things we recently working with a Coventry local council on the Innovative UK project for future energy potentials, and I think the aim is trying to reduce the cost by 20% and also clean, but really challenge, and really challenge, and I think all the solutions we put there, we analyze the system scenario from consumers' point of view, and also from investors' point of view, and also from DNO operators' point of view, to see from each angle what's the best solutions as the end. And I think if to avoid in the future is energy is clean, but people cannot afford, if some people, and I think it definitely needs some market structure change, and to move around the money, and then to give some kind of a profit for those operators, especially to encourage clean energy investors, and also to benefit the consumers. That's what I think from this particular project. It is not my area anyway. Yeah.
Absolutely, but thanks. That's a very useful comment, and I suppose this brings up the idea of when you put these costs into place, and the comments about markets, whether geography can play a role into this thinking, and with fuel poverty also in the mix there. I don't know, Bart, to what extent you think we can have targeted either technologies or locations where there's different incentives perhaps, or different market conditions to encourage storage that targets these kind of challenges.
Yeah, I suppose on a general level, fuel poverty is at the core of a lot of the government policy, whether it's storage or looking at other mechanisms. So certainly, I think considerations that will be looked at by policy colleagues, and certainly, again, I would use those consultation mechanisms to try and forward those ideas onto them as well. There are multiple ways at which government will try to deal with fuel poverty, but clearly ensuring that we don't end up supporting things that will create those kind of issues in futures is in the back of everyone's mind.
Thanks. And we've got a couple of questions on compressed air, where could be promising, but also what are the limitations there, and whether there's a question for Ji-hong specifically, it looks like value for money, but whether that's the best solution, what is the best solution associated with the heat storage problem to reheat the expanding air, thermal storage or hydrogen or something else. So it's mainly about the opportunity, but also some of the limitations and the potential solutions there.
Okay, and I'm doing two things because I'm invigilate my RACIT exam on another screen. If any student question, I will answer that. But I noticed Dr. Wei He is also in the audience. If I have to go to my exam session, Wei can answer the questions. I think about case, we did a lot of work about the case technology. It's a case, to be honest, and compared with 10 years ago, had made a great progress in terms of system efficiency improvement. 10 years ago, when we started working on case analysis, the energy efficiency probably around 40, no more than 50%, and also use a fossil fuel. But now the best system already in operation, and is over 60% round trip efficiency, and without using any fossil fuel. And so in terms of technology, it's keep improving, and certainly when people talking about 60% and compare with the battery with some others, still feel it's low. But if you think about sustainability and compressed air, everything, and you just use air as a medium to store. And now if there are quite a lot of work, and there's possibility to improve the system efficiency further and into 70%, there's a lot of work and very promising, and some demonstration project already in place in the process of constructions. And certainly in terms of research, we're also trying to find a way how it can improve the efficiency. In terms of energy density, yes, difficult to improve. It just need the largest volume of storage. But in the UK, we can a little bit relaxed on this aspect. I believe UK is fortunate. We have the geological conditions. We can making cost-effective storage volume, and the carbon lasts 50 years at least if you engineer in the van. And also we have a lot of gas stored in such kind of carbon, and when the gas gradually fades out, and certainly you can put hydrogen or others, but the compressor is another option, and for those currents. So that's my opinion on this gas. And I think it's mainly the case is a kind of very clean technology, sustainable, and a large scale, and you can store few days, and not any problem with very low leakage. Yeah.
Okay, thanks. There is a question endorsed as well about the extent of to what extent different scenarios for electrification of heat and transport affect energy storage options or and opportunities. So I wonder if any of the panelists have any comments, especially the ones presenting scenarios, future scenarios. So how these affect the options and opportunities, to what extent I suppose it affects decision making or our thinking about design of technology, selection of technologies, economies of scale. I suppose the question is, do we trust these scenarios? To what extent? I wonder if someone would like to comment.
I mean, I'm happy to take that one on, Alice. Again, I think in terms of electrification of transport, I think that is doing two things. I think clearly the electrification of transport, in particular cars, is driving battery development and technology and reducing cost. And clearly they're focused on technologies that hopefully will be safe, reliable, but also again meet particular metrics in terms of power and energy requirements for a drive cycle. Now, they might not therefore be the best technologies for grid use, particularly if it's not being cycled as much as it may in a car, or even partially cycled. But again, I think the main point about that is purely just the sense of scale just now. I think, as I said, the EV battery market is about 10 times the grid scale, and clearly if that's driving down lower cost cells, even if they might not be optimal for grid, I still think that's probably the way some of the grid storage will go in terms of using, if I can call it, transport type cells. In terms of electrification of heat, I'm going to digress slightly and actually make or explore not the direct electrification of heat in terms of electric heating elements as well, but more the use of hydrogen gas and heaters via that, and actually that development of replacing gas boilers with hydrogen boilers may ultimately give a competitive edge to fuel cell technology, because that might provide the rationale for large scale hydrogen production, which might ultimately favour again fuel cell vehicles, hydrogen fuel cell vehicles. Now, the slight caveat in that is that most hydrogen fuel cell vehicles are actually fuel cell battery hybrids. They generally tend to have a battery fraction on the car as well, for enabling startup initially and regenerative braking. So again, exactly how they might pass. I wish I knew, and then I could invest in one way or another. But currently, as I say, I think it just still comes down to a bit of a technology race between battery technologies per se and the battery versus fuel cell. Clearly, battery in the UK is by far and away the leading technology just now, but whether with the potential for replacing natural gas with hydrogen for heating, that might start to swing the scale back towards hydrogen fuel cells, potentially for transport as well.
Yeah, and Andrew, just to very briefly follow on from this, and to what extent is social acceptance of either these technologies or vehicle to grid been considered so far, and do you think this will be decision maker for?
Good question. I mean, I think there have been some interesting studies done on various safety elements, both from hydrogen safety point of view and from obviously the reported issues of batteries going in fire, etc. Ultimately, I think the general public will go with technology that is promoted, dare I say, promoted the best, which is a very fudgy term, because we go back to when petrol was the dominant fuel, and then the government promoted diesel. Clearly, there was a clear swing to using diesel, and there was advantages in that, until they then maybe perhaps realised that the technology from some manufacturers wasn't quite what was said on the tin, and clearly there was then other environmental issues from that. So again, I think the social acceptance on that can be driven the same way that the diesel, or change from petrol to diesel, was driven by both industry and government. So again, I think from my perspective, the jury's still out on which way that might go.
Okay, thanks, Andrew. That's very comprehensive. And there's one more question.
Can I share my opinion?
Yes, absolutely. Apologies. Yes.
Yeah. No problem. Yeah, thanks all the speakers and the panel members. Yeah, I fully agree with them that the one of the big challenge for for the zero future is that as Zhibin and Jihong presented, this is long duration or seasonal energy demand various, which may cause high demand in winter and probably low demand in summer. And clearly, for most of the energy storage technology for batteries, or even for compressed air, for pumped hydro, it's impossible to store energy for that long duration. So one thing, in my opinion, that that's power to X, or the fuel like hydrogen or methanol or ammonia will play a very important role in the future zero carbon scenario, because it is quite similar. The property itself is quite similar to conventional fuel. So I believe that this is going to play an important role. But on the other hand, the round trip efficiency of this chemical fuel, it's easy to store for very long duration, but the round trip efficiency is quite bad. So it's very likely that probably in future the combination of this this energy vector with other energy storage technology will play an important role. So take the compressed air energy storage as an example. The original concept of a compressed air is to decouple the gas turbine system, which still use the fossil fuel, natural gas. But then we move to a clean future. So nowadays, most of the compressed air energy storage focus on the pure compressed air. That is that no natural gas. But probably in the future, let's say the technology can go back, combine this conventional compressed air with this clean vector with, let's say, hydrogen or ammonia in this combustion process, so that this chemical storage or chemical fuel gonna play a role of long duration, stored energy from summer to winter, while, let's say, compressed air can meet the variation or meet the gap between, let's say, day or night or week and weekend. That might be something in the future if we fully banish all the conventional fossil fuel. And I also have something to share about the energy poverty. Is that it's very likely, in my opinion, that probably because currently most of energy comes from the fossil fuel, so the centralized generation, the centralized power supply play a very important role. And in future, if the renewable play a leading role, then the decentralized or distributed system, going to play a leading role. In this case, we're going to have some, let's say, you mentioned the region, probably is that we're going to have some energy rich region or energy poor region. And in this case, the storage probably going to play a very important role to balance this energy resource imbalance or probably things that might be something that we can think about as well.
Thanks, Yongliang. We've got one more question that I think will be forced to put through email, so I'll forward it to Angela. Just to mention it here, there's a question about integrated storage with power converters and how do we see the penetration of these, especially given the lack of definition of the grid code. I will park this question for now and ask the panel members to respond through email, but I've noted down the question and the name of the person, so we'll pick that up. I'd like to hand over to Yulong, but first of all, thank the panel members and the presenters for the wonderful presentations and discussions. And thanks everyone for the attention and excellent questions. I think that was a really good discussion. So thank you everyone, and over to you, Yulong.
Thank you, Harris, and thank you everyone, particularly our panel members and also our speakers, and which lay out all the numbers, which is I found, although I can't remember all those numbers, but it's clear. UK for sort of 100% renewables, we would need something like about 300 gigawatts storage. And think about 300 gigawatts storage. Globally today, it's about 200, maybe a bit more than 200 gigawatts installation globally. So, which is insufficient for the UK only. So if you multiply that sort of 200, 300 sort of gigawatts by hundreds, and so the opportunity is huge. So clearly there is a need for short-term storage batteries and electrochemical storage, and flywheel, probably the super caps for power grid quality. But there is a lot more needs for the medium term and long term, heat and cold storage, and also the flow batteries, for example, and so on and so forth, compressed air, liquid air, and so on and so forth. So clearly, we know the order of magnitude needs, both in UK and globally, but we actually don't know which technologies or which combination of technology will address that in the best way, in terms of economics, affordability, and sort of environmental impact lowest environmental impact. So lots of work to be done, and there's lots of sort of a bigger role for the storage to play in the future. So I'll conclude that and the meeting, and I thank all for your contribution, and also a specific thanks to the Bioenergy Hub people for coordinating, and also thanks to Angela and Harris to help with all those. Thank you all very much, and I think the session is closed. And there will be a session tomorrow, which is about the cross-hub collaborations, and welcome you all to attend as well in similar time. Thank you. Bye-bye.
Thanks, Yolong. Cheers.
Bye.